In this lecture, we're going to talk about a new definition of acids and bases. We've had our arrhenius definition, then our bronsted-lowry definition, which we've spent the most time on. And now we're going to introduce Lewis acid and base definition. So with Lewis acid and base, we're going to broaden our definition even more. So this definition will encompass all of our Bronsted-Lowry bases and all of our Arrhenius acids and bases as well. So it can apply to all of these. It's just a broader definition. And what it states is that a Lewis acid is a lone pair acceptor and a Lewis base is a lone pair donor. So we were really stuck on this idea of protons before moving around and that being a key part of an acid base reaction. But we find that actually a Lewis acid base is going to define it instead based on that lone pair that is contributing to the new bond that forms in the acid base reaction. And that'll be our focus of it. Which is interesting because what it really means is that a Lewis acid then, instead of being a proton, is just anything that has an empty orbital that can accept an electron pair, that's ready to form a bond where it doesn't contribute an electron, right? So like think back to valence bond theory, right? And when we were really looking at the structure of covalent molecules, if something had an empty orbital, right, that empty orbital can overlap with something with a filled lone pair orbital and form a bond. And that's what's happening in these Lewis acid and base reactions. If you think about what a proton is just a proton, right? Sorry. If you think about what a H plus ion is, it's just a proton. It has an empty s orbital. And that empty s orbital can accept the electron pair from a base. And so this is going to allow us to look at acids that are not just H plus ion, which is pretty cool. So in general, these Lewis acids have to be electron deficient. They're either going to be attached to an electronegative atom that is hogging all of the electron density, or they might not have a filled octet, something like that. So these are what we'll look for. Now, the Lewis base is going to be the part of the acid-base reaction that is donating that lone pair in, right? And so we've seen that. We've been tracking a base based on it has an available lone pair to participate in the reaction. And so that doesn't change. So our definition of a Lewis base here kind of stays a little bit more constant, which is nice. And so it's going to have just this lone pair that it can donate. In general, it means that this Lewis base has electrons that are shareable. So that means they're available, right? They're not spread out and delocalized over a thing, which, I mean, it could still do it, but it's harder. But they have to be readily accessible. So just comparing these a little bit more, where do we see these Lewis acids versus bases? So Lewis acids are going to tend to be molecules that are ions, positive ions, or have incomplete valence shells. So, H plus is a great example of something that doesn't have a complete valence shell. It's got no electrons in it, right? And it's an ion. It's a positive ion. Lewis acids can also be molecules or ions with multiple bonds that can shift around to accept more electrons. And so this one's a little bit harder to see and takes a little bit of practice. And it's okay if this is not something that you walk away from this class really good at identifying. It's all right. You'll get more practice in future chemistry classes. So multiple bonds will be able to shift to make room for electrons. And this becomes really important when we start thinking about organic chemistry and start looking at the mechanisms of which covalent molecules react. So which is why I say you can save this a little bit for a later day. We also see molecules or ions that have central atoms that can expand their octets can also act as a Lewis acid. Now, if we say that, then that really means that anything in the third row of the periodic table and below, can't spell below, will be Lewis acid, right? So that means chlorine can be a Lewis acid. Lots of things can be a Lewis acid. So think about that. Like a chlorine can be a Lewis acid. We typically think of it as having a lot of lone pairs and not having, that it doesn't fit, that fits more of our idea of a conjugate base, right? But it can expand its octet beyond 8 because it has access to those 3D orbitals that are empty in the same shell as its other valence electrons. So that means there's a lot of Lewis acids out there. A Lewis base is going to be any molecular ion that has an unshared electron pair, and they typically have complete shells. So you can look for that. Let's look at an example. So here we're going to look at our Lewis acid and a Lewis base. And so we have our Lewis base is going to be this NH3. It has that lone pair. And our Lewis acid is going to be this molecule BF3. Boron is one of our elements that has exceptions to the octet rule. It typically forms molecules such that it has 6 valence electrons around it. So it has an empty orbital, right? It doesn't have a filled octet. And so that empty orbital on the boron can accept the electrons from the nitrogen and form a new complex right here. And so this new complex that comes together in this reaction, this is called a coordinate covalent compound bond that's in between them. And we call this a Lewis base adduct. I know, we're going to throw new words at you. And so this bond is going to be different than when we talked about bonding before, which is like one element donates an electron, another element donates an electron. What we have here is one element's donating a totally empty orbital and the other one's donating 2 electrons in an orbital. And when they overlap, they form that coordinate covalent bond that is an adduct. And now this isn't isolated to just covalent, or sorry, non-metal elements at all. Like boron's a metalloid, but we see this in metal and non-metal interactions as well. And this is going to kind of form the basis of something we'll talk about in our next class, which is coordinate covalent bonds that form between something like a metal and a non-metal. We'll get these coordination compounds that do fascinating chemistry, and they tend to be beautifully colored, which makes them a little bit of fun. All right, here is another example. Here's an example of what happens when we shift around multiple bonds. So here we have a hydroxide ion, and this is going to be our Lewis base, right? And we have this lone pair that's ready to be shared, and it's got a negative charge, so it's like super accessible pair of electrons. And then we have carbon dioxide. Now, carbon and oxygen can't expand their octets. They're in the second row of the periodic table. But carbon has 2 sets of multiple bonds, which can move around and create space. And so what happens is a bond forms between the oxygen and the carbon, which is our Lewis acid right here. And we shift the bond. So some of the electrons that are shared between the carbon and oxygen, those, let's get a different color. So the electrons that are shared in this bond right here are going to shift and become a lone pair on our oxygen. And then we form a bond between an empty orbital on the carbon and a full orbital with a lone pair on the oxygen and create a coordinate covalent bond between that oxygen and carbon. We make HCO3 minus. Now, this is a key reaction in our body. This is respiration and the ability to maintain a blood buffer that keeps us at a safe pH in our bodies, that keeps us functioning, right? And this is a reversible process, right? And we think of it as the decomposition of HCO3 minus. No, scratch all this. Again, this is something that's going to play a large role in how we understand organic chemistry and mechanisms. And so this can really be a foundational piece for later work in chemistry. All right, let's just look at identifying a Lewis acid and Lewis base in these 2 reactions. So first we have NH3 and H+. So the NH3, I know there's a lone pair on that nitrogen, so that is going to make this my Lewis base. I'm still identifying Lewis bases the same way I was identifying bronsted-lowry bases, so that seems simple to me. It's nice. Now the H+, that is my bronsted-lowry acid, right? But I'm also noticing that it has no electrons. It has an empty orbital, and so this can act as a Lewis acid. And then we form an adduct, which is NH4+. Now let's look at the following one. We have BF3 and F-. Now my F- can't expand its octet. It's in that second row. So It's probably not going to be my Lewis acid because it has a lot of electrons and it's negatively charged. So this will be my Lewis base. Now my boron with my F3 boron has a incomplete octet at 6 here. And so it's going to be able to have an empty orbital that I can take advantage of. It has an incomplete octet. So it's going to be my Lewis acid and it'll form an adduct. And my hope is with Lewis acids and bases that you'll be able to work on identifying which would be the Lewis acid and which would be the Lewis base when I give you an acid base reaction at this level.